Hello class, welcome to the next lecture in our series online for the 8610 course. Today we're going to talk about panel data and difference in differences methods. Before we continue, a small disclaimer. I just got a new webcam to try and increase the quality of the sound because some of you said the sound was not very good. I've been trying to play with the settings on the recorder. I've been listening to what comes out of these recordings, and so please bear with me. Please don't get too impatient if the sound is bad. It will gradually get better as the lecture moves forward. Okay, let's get into it. Okay, here are some of the packages that we're going to use today. Before we head into the lecture, I'd like to say a few words on panel versus cross-section. So panel data means that you have the same sample with two observations or more over time. So the same individuals or the same items were surveyed. So data on the sample was collected twice or more, meaning that you can match the observations across time. Your observations are XITs, where I is the item or the individual. And so this is not the same as a repeated cross-section, where perhaps you have data at 2 points in time, but you don't actually have the same items or the same people in your data. So in a lot of the impact analysis literature, and particularly in randomized controlled trials, the most common panel is one observation before, one observation after the treatment. But of course, there are also multi-year panels. Once you have panel data, you can use a whole set of econometric strategies that are different from your simple cross-section. And the first one of those that I want to talk about is called first differences. Okay, so to introduce first differences, let us first think about this. Some variables do not vary over time, and others do. So imagine you have a 2-year panel of individuals, I, with variables x, y, and a. Let's say x and y both vary with time, so they are xit and yit. So this could be variables like a person's income, the hours they work, the employment status they have, their experience. But a is going to be a variable that does not vary with time. So we will just index a with an I without a t. So for instance, a person's ethnicity or talent or genetic material, those are things that don't change. If you survey them this year, survey them against next year, they don't change. Now, as most of the time in economics, what you want to do is know the impact of x on y. Let's assume for now that x is as good as random, but it depends on a. So for instance, let's think about y as being the wage, x as being education, and a as being gender. Education may change over time. You get a degree, a certification, you learn things. Gender, in most cases, does not change over time. But as we know from the gender gap literature, gender might affect the wage. And so you could run this as a simple regression where this t subscript t is a dummy for the period. You have a yit as your outcome variable, and here an intercept. Your covariates xit, so that would include education and maybe others, and ai, which would be your gender, that does not change, and then this dummy for the period. Assuming we only have 2 periods for now, before and after, your estimates will give you a twofold equation, right? In period 1, you interpret it as yi is equal to alpha plus beta x plus gamma a, plus that error term, and in the second period, you have the same thing plus tau. What does tau do here? Tau actually just shifts the intercept for the second period, for tt equals 1. Okay, so all of that is well and good, but imagine now for a second that you don't actually know how to measure a. Instead of something like gender, which we can see and measure, let's have it be something like ability. So this is again a classic example, a regression of wage on someone's education plus their innate abilities. Well, the problem is we don't really know this. So we can't really see ability, but we know that is important in this equation. Because if we don't control for it, our beta will be biased. And so the trick here is the first difference, your twofold equation. You think of it as the following. your equation in the second year minus your equation in the first year. If you subtract one from the other, you get yi2 minus yi1 equals beta times the difference between xi2 and xi1 plus the tau plus the difference in error terms. But look what happened, a disappeared. So by first differencing, what you did is you've rid yourself of the problem of unobserved fixed characteristics, such as ability, for instance. Now, an important thing to note is that the beta parameter and the tau parameter that you're estimating are still exactly the same as in your first equation, meaning you are estimating them as if you knew the unobserved a, even though you actually don't. So beta is still beta, and now tau is just the intercept of your first difference equation, right? There's no alpha here, the alpha dropped out. Of course, all of this is assuming that your model was correct apart from a. You still need to get the correct x's in there. So the point here was to get rid of this time invariant heterogeneity. We did it with the example of a, your ability, but actually it means that you got rid of all of the fixed characteristics of your individuals. Any characteristic that is fixed over time, whether you actually observe it or you don't observe it, drops out of the equation. So in an equation that is first difference, for instance, you cannot control for things like ethnicity that don't change. Those will drop out of your equation no matter what. Even though you do observe them, they get differenced out. So first differencing, this is one way of thinking about how to get rid of this time invariant heterogeneity. Now there's a second way to do that, to think about those. And that second way is fixed effects. Okay, so the second thing that's useful to do with panel data is fixed effects. Adding fixed effects can be thought of as just adding dummies. Think about this original equation we had, which we said was actually split into a twofold specification with a different specification for y1 in the first period and a second specification in y2 for the second period. The difference between these two was this tau term right here, which only appears in the second period when tt equals 1. So in the first period, the intercept is just alpha, and in the second period, the intercept is alpha plus tau. And tau captures the difference in the average y in the second period compared to the first period. So when you added this t dummy to your regression, what you did is you captured the period fixed effect, the effect of being in period 2 compared to being in period 1. So when you added this t dummy to your regression, what you did is you captured the period fixed effect. That is the average effect on y of being in the second period compared to the first. Okay, so now let's think about adding individual fixed effects. A fixed effect for each individual in your panel, for each I in your panel. So here the same principle will apply. The same way that you added a t dummy for the second period, which was equal to 1 for the second period and 0 otherwise, so in the first period, you can add individual dummies where the dummy is equal, the I dummy is equal to 1 for individual I and 0 for everybody else. In the equation, it looks like this. You're still regressing y on all of these terms, and you add a series of dummies. There are as many of these I dummies as you have individuals in your panel. And each of them gets its own delta coefficient in the regression. Okay, but wait, what happens to AI in that case? Well, AI has become a linear combination of the fixed effects dummies. To see that, just think about it this way. The vector AI is the vector of values A1, A2, A3, etc., until your last individual AN. This is A for individual 1, this is A for individual 2, etc. Okay, but A1 can be thought of as A1 times 1 plus A2 times 0 plus A3 times 0, etc., plus AN times 0. Okay, the same thing with A2. It's A1 times 0 plus A2 times 1 plus A3 times 0, etc. And A3 the same way, and AN the same way. So if you have a dummy variable here that is 1 for individual 1 and 0 for everybody else. And here a second dummy that is 1 for individual 2 and 0 for everybody else, etc., until the dummy n, which is 1 for individual n and 0 for everybody else. Well, you've created a linear combination of a1 times I1 plus a2 times I2 plus a3 times I3 plus an times in, which is actually equal to your a vector. And so the ai term is now redundant in the regression. And the same goes with alpha. It's a linear combination of these dummies now. And so what we find is that once we add the dummies, this original regression, which had a and alpha in here, simplifies because the delta i's pick up alpha plus gamma ai. And so you've simplified those terms to where the ai and the alpha dropped out. And so what happened, we have absorbed the time invariant characteristics of the individuals. And again, we get the same beta estimate as we had before. So importantly here, what's happening is that with two periods, first difference and fixed effects are exactly the same. We saw with the equations that they actually give us the same beta. They are two equivalent specifications. Now, with more periods, it's a little bit different. If you have more than two periods, FD is more tedious because you have to compute standard errors that correct for the serial autocorrelation, and you don't have to worry about that with FE, with fixed effects. And so the rule of thumb is that usually people will prefer to go with fixed effects. Okay, so to finish this part about fixed effects and first differences, let us do a quick demo of what this looks like in R. So first of all, we're going to make some fake two-period data. So our data looks like this. We're going to take n observations. So this is the kind of data we're going to make. We're going to take n observations with n equal 1000 of a random variable, which we make a normal of 100 mean and standard deviation 20. So we take 1000 observations of this standard normal. That's our fake first year data. For the second year, for x2, we're just going to reproduce this x1, and we're going to add a normally distributed error on top of that with mean 10 and standard deviation 2. Our a variable is going to be another standard normal with mean 8 and standard deviation 4. These numbers don't mean anything. They are just recognizable values for me. We're going to set alpha to 50, beta to 11, gamma to 22, tau to 20, tau to 33. And so we're going to create y1 and y2 in a way that exactly matches that theoretical model. It's equal to alpha plus beta x plus gamma a plus tau, but tau only appears in period 2. So this is exactly the data that we are expecting to get from our earlier specification. So this code up here just concatenates everything and makes a little data frame with this, but look what the data looks like. We have an identifier for each individual. That's individual 1, period 2, individual 2, period 1, period 2, individual 3, period 1, period 2, etc. We got the y variable, we got the x variable, we got the a variable, which as you notice does not change between period 1 and 2 for every individual. And then we have a t dummy. This is first period, this is second period, etc. So let us simply run the 4 regressions that we talked about today. The first regression we talked about today was if we happen to observe the a variable, the time invariant variable, we would just run y on x and a and t. So we call this model a obs for a being observed. If we did not observe a, we would do the same thing, but obviously we would not know how to include the variable a. We'll call this a unobserved. So now, if we suspect that a exists, but we don't have the data, we want to control for it, we want to control for the unobserved fixed characteristics, we are going to run a first difference model. How do we run the first difference model? we just compute the first difference in y, y2 minus y1, the first difference in x, x2 minus x1, and we run a model of dy over dx. Remember, the lm command is just an OLS command. It runs a regular OLS regression. The last thing we do is that we want to have a fixed effects model. A fixed effect model cannot be run with the lm command. It has to be run with the plm command. So we downloaded the plm package, and now we can run plm of y on x and t, and nothing else. Again, we don't know a, we assume we don't know it, so we cannot include it in our regression. The one more thing we add is index equals id. This means I want fixed effects for each id in my sample. So these are individual fixed effects. This is the code to produce our table. I use the Stargazer package here. I'm leaving this on just so you can read it for a few seconds. This is what it produces. We have our first OLS. In the lucky case where we observe A, we can just include it in the regression, and so we find exactly what we were expecting. We define y as being 11 times x plus 22 times a plus 33 times t, and we find exactly the three coefficients with perfect match. And remember, we defined the constant as alpha being equal to 50. This also matches, and our adjusted r squared is perfect. But now look what happened in the second equation. We didn't know a, and we ignored it, so we get a biased beta, we get a biased tau, and we get a biased constant. And of course the r squared does not match perfectly. But if we use either of our specifications that take advantage of the panel nature of the data to get rid of unobserved heterogeneity, or to get rid of time invariant characteristics such as a, then with the first difference we get 11 as the coefficient on the dx, and we get the constant that jumps in and picks up the role of tau here. Then the 22 disappears and the alpha disappear. And here, look, in this fixed effects model, we get the coefficient on x being the same one, the coefficient on t, the tau, being the same one as before, and we lost the need for controlling for a. And even though we did not control for a, we are getting the correct coefficients. And the adjusted r squared shows that we also have a perfectly matching model once again. So let's wrap up on first differences and fixed effects. First differences and fixed effects are both methods that help you deal with time invariant unobserved heterogeneity. That is just jargon to say characteristics that are fixed over time. So with two periods, those two are exactly the same, but with more than two periods, they're not the same, and most of the time people prefer to go with fixed effects. Now, another thing I should say is that fixed effect is sometimes called deviations from means model. So I introduced fixed effects as being the same thing as just adding dummies. But that's not actually the formal definition. That's just a way that I think is convenient for thinking about these models. Actually, the more formal definition computes deviations from means. It's called demeaning. If you check any good textbook, they will present the fixed effect model in that way. And in particular, the mostly harmless econometrics in chapter 5 explains very well why the fixed effects model is actually a deviations from means model. Okay, so the third important technique I'd like to talk about is called difference in differences. That's also a technique that you use when you have at least 2 years of data. Though for difference in differences, it doesn't actually have to be panel, though most of the time it is. So let us first repeat something we said in an earlier lecture, which is that in a perfect experiment with perfect randomization, the difference in outcome at the end after the experiment measures the actual impact of the treatment. And that is because under true perfect randomization, pre-treatment all of your individuals are completely indistinguishable, and then some of them randomly get assigned to the control group, others to the treatment group, and the difference between the two is the observed difference, and it does measure the average treatment on the treated, and the selection bias is 0. You can look up that slide in the previous lecture. It's the same slide. But unfortunately, of course, most of the time things are less than perfect. So for instance, are your treated and your control samples truly indistinguishable? Probably they are not. They must differ in some way. And the real problem is that you will never know, because even if they are completely indistinguishable on all of the observables that you can think of, well, what about the unobservables? Treated and control may differ in ways that you will never know about. And so panel data can help here as well. So let us look at this picture. So this is the basic setup for a difference in difference specification. You have the before data, you have the after data, and you treated sometime in between the two data collection events. Now, maybe the two groups were a bit different to begin with. This is seen by the difference between yi before for the control group and yi before for the treated group. We see that there is a difference. Let us call this the before delta. Now we imagine that it is possible that between before and after the variable of interest would have changed, but the same way there was a difference before, well, we would still have the same difference. So we would still have the same difference between the yi after for the control group and the yi0 after for the treatment group. 0 here meaning this is the hypothetical that would have happened if they had not been treated. So these are 4 data points of which we only know 3. We know these two, this one, but not this one. This one is not observed. This is the hypothetical, the potential. What we actually observe instead is this. We observe the y for the treated given that they were treated after the treatment. And the average effect of treatment on the treated is the difference, again, between this actual y1 that happened for the treated group and the potential y0 that would have happened for the treatment group if they had not been treated. But so the key to the differences in differences is that we observe this green arrow, the difference between the two groups after the treatment, and we observed the difference here, the orange arrow, which was the difference between the two groups before treatment. But graphically, it appears clearly that the average impact of treatment on the treated is just the difference between the after delta and the orange arrow, which is the before delta. So after delta minus before delta is the average treatment on the treated. That is the difference in the differences. So there are actually 2 ways to get the intuition for this. Either you can think of this as the difference between the before gap and the after gap between the two groups, which is what we just saw on the previous slide, or what I'm going to show on the next slide, the difference between how things changed for the first group and how things changed for the other group. Mathematically, those are exactly the same. So here, your difference in difference is the after gap minus the before gap. This is the difference in those two differences, but equivalently, if you just move the blue item here and the red item here without changing their signs, you've reinterpreted this as the difference that happened for the first group between before and after, and the difference between before and after for the second group. And so this is also the difference in the differences, but it's reversed. You can see that on this graph, which shows the second way of thinking about the intuition here. I think that is a little less compelling graphically, but I think the intuition is very good. The difference between how things changed for the two groups. So the gray arrow is how things changed for the non-treated group. The purple arrow is how things changed for the treated group. And the average treatment on the treated is actually the difference between the gray arrow and the purple arrow. It's not as obvious graphically, but we just saw that mathematically this is exactly the same. Okay, so in between the previous slide and this slide, I tried to fix the sound, so hopefully now you won't be hearing all this background noise when I talk. Okay, so let's go back to the slide. how would you actually compute a difference in difference estimator? Well, you can simply do it by hand, right? You can compute the averages for the 4 groups. You can compute the averages that correspond to these 4 points that I showed you on the previous slides, and then just subtract them. Take the first difference and then take the second difference, and you have your difference in difference estimator. If you look at this 1994 paper by Card and Kruger, which you, by the way, will reproduce in your homework, you see that this is exactly what they do. So they have a treatment which is a shock to the minimum wage. It happens in New Jersey, but not in Pennsylvania. And so they have data for Pennsylvania before and after. They have data for New Jersey before and after. And then they take the difference for Pennsylvania, they take the difference for New Jersey, and then they take the difference between those 2 differences. And of course, reciprocally, you can have the difference between Pennsylvania and New Jersey before, the difference between Pennsylvania and New Jersey after, and the difference of these differences is the same number which you find in this corner. And so one of the exercises you'll have to do in your homework is to reproduce this number in this corner. Now, there are a few problems with doing difference and difference by hand, and that is that, first of all, computing the standard errors gets tedious pretty quickly, and it is subject to some problems when you have heteroscedasticity and all these kinds of unfriendly data properties. The simplest option to compute this standard error is this formula, where you take the 2 standard errors, and each of them is squared and divided by the number, the sample size. You have n1 and n2, which reminds you that you don't actually need to have the same number of observations in both the treated and the control group. But the bigger problem with doing difference and difference by hand is that you cannot control for the other confounders that might exist in your data. And so that is why we usually do this with a regression. Okay, so the first thing we can do, one of the first things we can do, is to just do a simple regression with a differenced y, variable. This is because we have 2 groups, the treated and the non-treated, and we have the same individuals surveyed before and after the treatment. So we can compute the first difference in y, the delta y, which is yi2 minus yi1 for each individual. And then if we just regress the delta yi on a group dummy, which is 0 for the non-treated and 1 for the treated, we call that di, well, we get delta yi is equal to tau plus gamma di. So we have all the delta y's, which are the before-after differences in the y variable. Now we regress this and we get tau, which is the intercept for the group that has di equals 0, so the non-treated. So this is the average before-after difference in y for the untreated. Now when di equals 1, the equation becomes tau plus gamma, that is the intercept for di equals 1, and so that is the average before-after difference in y for the treated. Now you see you have tau for the non-treated, tau plus gamma for the treated, and so gamma is the difference in the differences. So this regression gives you the same result as doing the difference in difference by hand. And in this case, you could actually add regressors at the end of this equation to control for other variables. However, almost nobody does it this way. The actual classic difference in difference regression specification is the one I'm going to show you on the next slide. So the classic difference in difference regression is one that you actually run when your data is in long form. So you do not first difference, you keep it stacked. So let's imagine this to be a 2-period diff regression. On your left-hand side, you have yit, I is the individual, t is the period before and after. And so you regress that on an intercept, a dummy for the group, a dummy for the time period, and, this is the key, an interaction term between the group dummy and the period dummy. So this intercept term is equal to 0 for the control group. It's equal to 0 in the first period. It's only equal to 1 for the treated group in the post-treatment period, in the after period. Note that when you do things this way, you don't technically need panel data to run this. Most of the time, You do, but this is actually a repeated cross-section specification. So how do you interpret those coefficients? Well, alpha here is the mean for the untreated before treatment. How do you see that? For the untreated before treatment, D is 0, T is 0. This interaction term is also 0. And so the non-treated in the first period just get alpha as their mean. Now, when D equals 1, beta kicks in. And so beta shifts the intercept for the treated, but before the treatment only. Tau, on the other hand, shifts the intercept in the after period for the untreated. And finally, gamma shifts the intercept for the treated, T equals 1, after the treatment, T equals 1. And so again, gamma is actually the treatment on the treated, the average effect of treatment on the treated. That is our coefficient of interest, because that represents the difference in the mean for the treated group after the treatment. Let us do this interpretation again in slightly different words. Maybe this will work better for some of you. Alpha is just the baseline mean. Beta is the coefficient that will account for the treated group being slightly different to begin with. Remember that orange bar we used to have on the plot. Tau is what accounts for the time trend, so that accounts for the fact that the second period is different than the first period on average. And now gamma is the actual effect of the treatment. It is what shifts Y for the treated after the treatment net of the time effect. So it's the difference in differences. Okay, but actually we have a little bit of a problem here called the parallel trends assumption. That is the assumption that we're making. So remember that at the top what we said was something that sounded like maybe the two groups were different to begin with. Was this orange arrow. Without the treatment, they would still have the same difference. We said that. Well, that is not that innocent at all. It is called the parallel trends assumption. So remember our hospital example, and we'll see why this assumption is a little problematic. So sick people have lower health to begin with. Okay, that's our orange difference. That's our before delta. Let's say it's 20%. Sick people, let's say, have 20% lower health on average than healthy people on this health score. So without going to the hospital, would that difference stay at 20%? Or would these sick people recover? Or maybe they would get worse. But the assumption that this difference between the sick people and the healthy people would remain the same if the sick people didn't go to the hospital doesn't really hold. In other words, the trends for the two groups are not actually parallel. Now, of course, this is an extreme example. In real life, we try to have groups that are as close as possible and not as obviously different as sick people versus healthy people. However, we don't know whether the groups might be very different on unobservables, right? And so this kind of extreme example shows us why this is problematic to begin with. So graphically, it's easier to look at it this way. So remember, this is the same picture that we had before, except previously we didn't really think that this treatment happened somewhere in between what we observed before and what we observe after. Actually, we are assuming that what is happening is that we observed some data before, and everything continues to trend normally until we treat the treated group. And then the trend for the treated group changes and it ends up in a different spot than it would otherwise have. Of course, we don't actually observe this, so we are not able to say anything about it. But when we make the parallel trend assumption, we assume that had they not been treated here to deviate from the trend, they would have landed there, right here, at the same distance that they used to be from the non-treated. That is the parallel trend assumption. And the important thing is that the average treatment on the treated and the difference in difference estimator are this red arrow, right? They are the difference between what you observe and what you would have observed. Now, of course, if they actually were not on a parallel trend, then your estimation doesn't work. Imagine something like this. The treated group was not on the same trend as the non-treated group. Their trend was a lot steeper. And so they would have ended up here if you had not treated them, very close to the non-treated. However, you make the assumption that this orange arrow remains unchanged, and so your difference in difference estimator tells you the average treatment on the treated is this small with the purple arrow, when in fact it is this large with the red arrow. And so as you see, if your parallel trends assumption does not hold, your diff and diff estimator is nowhere near the actual real treatment on the treated effect. Okay, so how would you actually test for this parallel trend? Well, tough luck. When you have two periods, you actually can test for it. You can try to add covariates, hoping that the parallel trends hold once you control for all the other covariates, for the observable covariates, but you will never really know if it holds. So then your specification is the same, you just add some covariates here, often are called XIT. Now, if you have more periods, you can actually start doing some testing, because you can test whether the trends for your two groups were parallel before you actually got to your treatment. Okay, so now that we've seen all of this, let us talk about a few extensions of this simple classical DiD framework. The first one I want to talk about is a difference in difference with multiple groups and multiple time periods. So now you imagine that T has more than two values, and you imagine that G might also have more than two values. So you can have maybe 3, maybe 5, maybe 10 groups, and you can have as many years as you want. And so the different groups get different treatment at different times. This is important. You want to allow for this. You want to allow for different treatment groups to be treated at different times. Okay, so the equation actually stays almost the same. What you have now is a YIGT, so G the group, T the period, I the individual. And you regress that on a set of dummies for each group, a set of dummies for each period, and the J's are kind of playing the same role as our interaction term now. They are equal to 1 for a given group in a given time period if they were treated at that period. So they are like this interaction term, but now you have many, many of them. And of course, they're equal to 0 for everybody else in every other time period. Of course, you can add covariates here, again, the XIGTs if you want. But again, in this specification, it is this gamma on these interaction terms. This is what gives us the diff and diff impact. Here's another nice extension, what we call the triple difference estimator, or difference in differences in differences, or triple D sometimes called. So you do that when you worry that your groups are not comparable enough. So in other words, this is yet another way to try and get at this parallel trends assumption. So here's an example from a famous paper by Gruber that came out in the AER in 1994. So the Y variable here were wages. So Gruber is looking at the impact on wages of the treatment, which were laws that give mandatory maternity benefits to women. Now in this paper you have states that were treated, such as New Jersey, Illinois, New York, that had maternity benefit laws, and control states like Ohio, Indiana, Connecticut, North Carolina, and Massachusetts that did not have maternity benefit laws. Now the worry is that these 3 states are fairly different from those 5 states, and that you cannot actually treat them as if they were having parallel trends in terms of their wages, even without this treatment. And so what do? You add one more level of difference, and that level is women versus men. So what's the logic here? The idea is that even if the trends in wages themselves may differ between states, we might assume that the trends in the men-women difference in wages, meaning the wage gaps, might not differ. So the wage gap might exhibit parallel trends in the absence of the treatment. However, the treatment should affect that difference. Why? Because the maternity laws would affect women, but they would not affect men. So the men serve as a placebo. In a way, this is like taking the difference between the real difference in difference estimator, which is the difference in differences for women, and a placebo difference in difference, which is a difference in difference estimator for the men, which by definition would not be affected by that law. Another way to think about this is that it is just like taking a difference in difference estimator, but where y is a gap instead of just a level of a variable. So instead of doing a difference in difference on a wage, you're doing a difference in difference on a wage gap. So what is the triple difference equation? Well, it's the same principle, but you have more dummies and more interaction. So now you have a D that is the treatment dummy, a T that is your period dummy before, after, and a G that is your gender dummy, male and female. So here I dropped the I's and the T subscripts to make it a little more legible, but in essence what you are estimating is Y on alpha plus the treatment dummy, the period dummy, the gender dummy, and the two dummies interaction, treatment period, treatment gender, and period gender. And finally, the triple interaction, the treatment dummy times the period dummy times the gender dummy, which will only be equal to 1 for the women in the treated period for the treatment group. So again, this now carries this gamma that is going to be our estimator of the average treatment effect, because gamma is the shifter of the intercept, the shifter of the average for the treatment group in the treatment period, netting out the placebo effect. If you want to know more about this triple difference equation, I suggest you click on this link and get Imbens's lecture notes. He explains the concepts quite clearly. Okay, and so now just wrapping it up, let us just touch on a few more advanced topics on differences and differences. What you need to know is that this methodology continues to develop currently, and so I want you to know about a few of these. So the first one is a discussion that started with Bertrand et al. In 2004 with a paper in the QJE called How Much Should We Trust Differences in Differences Estimate. So the problem that they point out is that when you have differences in differences in multiple periods, you can have serial correlation in between the periods, and how the classical diff-in-diff regression specification does not account for this serial correlation, and so it leads to inconsistent estimators. The second relevant discussion that you should be aware of is the one on changes in changes. So Althi and Imbens in 2006 pointed out that you can actually estimate shifts in the entire distribution instead of just looking at the shift in the average effect. And so they proposed an estimator to do that, and they call it the changes in changes estimator rather than the difference in difference estimator. Now there is quite recent work on diff-in-diff with multiple time periods. Here, Callaway and Santana have a working paper called Difference in Differences with Multiple Time Periods. They propose a method to deal with these parallel trends. And importantly, they made an R package that is called DiD, which you can download, and you can use the estimators that they propose. And finally, this paper from last year by Egami and Yamauchi called How to Improve Difference in Differences Design with Multiple Pre-Treatment Periods. So this working paper is almost entirely about how to deal with parallel trends. Here you see these plots that are slightly, that look very similar to what I showed you earlier, but actually what they are talking about is you have two periods of data here before your treatment. So we used to focus just on this. If you have one more period before that, then you can look at your parallel trends assumption, and they develop the concept further. They introduce the extended parallel trends assumption, the parallel trends and trends assumption, etc. So if you are interested in this, I encourage you to read these papers, and in either case you should be aware that these discussions are happening. And this wraps up our lecture for today about panel data and differences in differences. A lot of what I showed today should be very helpful for you to complete your homework. If you have any questions, please let me know.